Hi everyone, here we'll discuss about a hydraulic jump as an energy dissipator at the bottom of a spillway. As we know, when water flows over a spillway, at the bottom of the spillway or at the toe, its velocity remains really high. So we need to dissipate that energy, the kinetic energy, by some means. So a hydraulic jump is a very useful tool, very effective tool for this dissipation of energy. Now let's refresh the equation of the hydraulic jump, where we had this kind of an equation where y2, that is the downstream depth of the jump, is given by y1 by 2 minus 1 and so on, where y1 is the depth just before formation of the jump in the upstream, that is this one, and fr1 is the Froude's number at this location just before formation of the jump. The equation can be written in this form also, where y1 can be found if we know y2 and the Froude's number at this point. So to get y2 we need y1, or to get y1 we need y2, but at least one of them should be known. Now how to get that value? We'll keep this formula here for reference. Now, so determination of sequent depth. Depth at the toe of the spillway can be obtained by the energy equation. By energy equation, which basically means this: the total energy behind the spillway must be equal to the total energy at the toe of the spillway, that is when the water has flown to the downstream, plus whatever losses have occurred. That is H. H is the total depth of water in the upstream, and small h is the depth of water. It's very small depth at the downstream, at the toe of the spillway, plus whatever is the kinetic energy. You see, in the upstream we are not writing any kinetic energy because it's almost negligible, because in upstream of the spillway the velocity of water is very less. It's a large reservoir, so it is almost stationary water, and whatever losses have occurred when water is flowing over the spillway because of friction with the spillway walls or with the atmosphere or due to the turbulence of the water itself. Now from this equation you can find out what is this H. That part you will do yourself. Now in the downstream, this part of the channel will have some slope, some Manning's coefficient, and based on the charge it will have some depth y. Now let's call that depth equal to yn, or let's suppose this is the normal depth. Normal depth means for a given value of the charge, given Manning's coefficient and given slope, the water will flow at a given uniform depth or normal depth. So under undisturbed condition, this will be the depth available at the downstream. That means this y2 has to be equal to this normal depth. Now when water is flowing here, at this point the depth is very small, that means velocity is very high, and it is most likely that it will be a supercritical flow. Now when this supercritical flow is occurring, based on whether this part of the channel is mild sloped or horizontal and so on, it will be either an M3 profile or H3 profile, like that. So if you remember those kind of profiles, they were increasing in depth as we move along the positive direction of flow. So this way the depth of flow will increase slowly along this kind of a curve. Now at some point this depth will become equal to this depth y1, that is the depth required for formation of the jump. Let's say that depth becomes equal to y1 at this location. That means at this point itself the jump will form and we'll get this kind of a hydraulic jump. So Therefore, we can conclude that the jump occurs at a location where the depth of the GVF profile, you see, this is a gradually varied flow profile, right? It becomes equal to the upstream sequent depth y1, satisfying this equation y1 equal to so and so. Now, as y2 decreases, if this depth is less, then what will happen is y1 will increase. From the formula we can verify that. If y1 increases, that means this length of the profile will have to increase. That means if we required a small y1, then the jump will form here. If we require a bigger y1, then the jump will form around here. That is, the GVF profile length will increase to reach the required y1. The problem with that is, here the flow velocity is very high in this portion, and therefore a long portion of this river bed will require to be protected against the scouring action of the fast moving supercritical flow. So we obviously would want to avoid that. Now let's search for an optimum solution. As y2 increases now, if y2 increases, then y1 will decrease and the jump will occur closer and closer to the spillway. If y2 is very small, then y1 will be large and the jump will occur very far from the spillway. If we keep on increasing this depth y2, then the jump will occur closer and closer to the spillway. So approximately here. So this will become y1, and given that we have a y2 of this much amount. So for a particular value of y2, the jump will occur at the toe of the spillway, very close to the toe of the spillway. So we would mostly want that value of y2 to remain in this downstream portion of the spillway. So in that case, only a small length of the river bed requires to be protected. So here the velocity is very high, so this area obviously has to be protected, and in the jump there is lots of turbulence, so we have to protect almost this much length. So this is the optimum location for the hydraulic jump. Now as y2 increases further, the problem is the jump will move further and further upstream. So if we increase the downstream depth y2 too much, then the jump would want to form here, but it cannot form here because there is a spillway, there is no water here. In that case, the jump will be submerged under the large depth of this downstream water, this tailwater, and therefore some kind of rolling flow occurs actually. So here the jump is submerged underwater, so the required amount of turbulence cannot happen and this kind of large eddies will form. The problem with these large eddies, large rolling currents, is that this is not very efficient in dissipating the energy. If there is small eddies, those eddies will be affected by friction and they will lose the kinetic energy, lose their energy to the atmosphere through friction. But if it's a very large eddy, then it will not be affected by friction that much and this energy will be preserved and that energy will be carried to the downstream. If we further increase this energy, this downstream depth, then instead of a submerged jump, we'll have this kind of a standing wave. So these kind of waves are formed, and if we even increase even further, then this kind of waves will be formed. This is called a standing wave. Here also these are called standing waves because the waves appear to be stationary. That is, this wave doesn't move, only the water moves. But generally, in case of spillways, we do not reach this condition or this condition. But there is a possibility that we'll reach this submerged jump, because definitely the spillway is a very high structure and downstream depth is not likely to be this high. It is generally in this range. Now, how do we create the jump at the optimum location, suppose? So the depth at the toe depends on discharge. So based on the discharge, you can find out what is the depth h here. If we want to create the jump right at this position, then that h needs to be equal to the upstream sequent depth of the jump required, which is y1, and the available tailwater depth needs to be equal to y2, this depth. But the problem is the downstream depth available may not be equal to y2, it may be some other depth, y2 dash, and that will depend on the downstream conditions, such as for a given discharge, bed slope, Manning's coefficient, the tailwater depth will be equal to the normal depth for that particular discharge, and which may not be equal to the sequent depth required. So it is some other depth. It may be less than the required depth, or it may be more than the required depth. Now let's explore those options. If the available depth y2 dash is less than the required depth y2, then we can artificially increase the downstream depth so that the jump is formed. We can do that either by lowering the floor by some calculated amount like this. You see here the depth at this point is less than the required depth. So we have lowered the floor near the spillway so that the available depth is greater and is equal to the required depth y2. So the jump is formed very close to the spillway. There is another solution by raising the downstream water level using a weir of calculated height. Sometimes that weir is also called a baffle wall. So this kind of a small weir or baffle is provided so that otherwise if water would flow at this depth, now since it has to pass over this weir, it has to increase its own height to attain some kind of head, some amount of head, and by that we have increased the depth to the required amount, and now again the jump is forming very close to the spillway. The other situation is that if the required depth is more than if the available depth is more than the required depth, so in that case we need to artificially decrease the downstream depth. Otherwise, a submerged jump will form, those rolling currents will form, and the energy will not be properly dissipated. So that can be done by providing a sloping apron or a ramp or glacis. They're all the same things with different names. So if this is the spillway, the bottom of the spillway is provided with this kind of a sloping apron, which is also called a glacis or a ramp. So what happens here is, if this is the depth available, which is more than the required depth y2, this is y2 dash, but we only required y2 amount. So somewhere along this ramp, as you see, if we measure the depth here, the depth will be less than this depth. So somewhere around here, the depth will be equal to the required depth, which is less than the available depth. So for this depth, the hydraulic jump will form like this. So this is how we solve that problem. Now another problem is to address the variable discharge. You see, this problem, this solution, or the previous solutions where we provided a depressed floor or a weir or baffle, they were the solutions for one particular value of discharge, which is the design discharge. That is the maximum discharge possible. But the discharge may be less than that. We cannot only design for the maximum discharge. If a smaller discharge comes, then what will be the situation? whether the downstream depth will be less than required or more than required. So for that, we need to take help of some other tools. One is called the hydraulic jump rating curve. We can call it jump rating curve or JRC. It will look something like this. So it is a plot between discharge and the downstream sequent depth Y2. That is, when Q increases, discharge increases. The corresponding downstream sequent depth required for formation of the jump also increases. The other tool, the other curve is the tail water rating curve. It will also have a shape like this. Now this is the curve between the discharge and the available depth at the downstream or the tail water depth. This is not the required depth. This is the depth which is actually available. So it is the plot between discharge and the tail water depth Y2 dash, and it also increases with discharge. Now both of them will increase at different rates. Now we need to compare them. So there may be several situations when the tail water rating curve is below the jump rating curve. That means this situation. So for the entire range of discharge, this available depth is less than the required depth, which means we have to increase the depth for the entire range of discharge. So this solution or this solution will work. Now, when that tail water rating curve is above the jump rating curve, that means the available water depth is greater than what was required for the jump. In that case, this solution will be applicable, because here we are reducing the tail water depth so that it becomes equal to the required jump depth. Now some two other situations may be faced. One is when the tail water rating curve is below the jump rating curve for smaller discharges, but above the jump rating curve for higher discharges. So if the situation is like this, that means for smaller discharges, the available depth is less than the depth required, and for larger discharges, the available depth is more than the required depth. Or the opposite can happen when the available depth is more than the jump depth required for smaller discharges, and vice versa. So in that case, we need to combine the previous solutions, and this kind of an arrangement can be made. That is, when the available depth is more than the required depth, the jump will form somewhere around here, and if it is less than the required depth, then the jump will form because we have reduced the floor height and increased the water depth. So this is how we solve that problem. Now we'll briefly discuss a small topic which is called the stilling basin and addressing the length of the jump. You see, the jump also has a length from here to here. That is, in this part there will be lots of turbulence, and that turbulence can also lead to lots of erosion in the riverbed. So all these solutions, this part is called a stilling basin. Here this part will be called a stilling basin. Here this part can be called like a stilling basin, and here this part can be called a stilling basin. So this length of the stilling basin, how large it should be, it will be decided based on the length of the jump. And if we provide these kind of roughness elements, these are called baffle blocks or chute blocks. So they will reduce the turbulence, they will reduce the velocity of water in the lower portion of the bed, and this way they will reduce the length of the jump, and the jump will be contained within a smaller length in the downstream. So you don't have to provide lots of protection for a very long length like this. Another problem is, we are not going to address it here. That is, what kind of jump will form. We have discussed weak jump, strong jump, steady jump, oscillating jump, and so on. If the jump forms like this, if it continues for a very long duration, length, then that kind of jump is not suitable actually. So we need to adjust the Froude number somewhere in this location so that the desired type of jump, which is generally a steady jump, where it's very well defined like this. This kind of a jump is provided. It's efficient, and at the same time it is not having a very large length. So that can be done by adjusting where exactly in this location, in this portion, the jump is formed. This is just to give you an idea of the advanced concepts of this energy dissipation, but we are not going to address it in this video, maybe sometimes later. So that's all for this one. Thank you.